Hello everyone, welcome to the OneClass channel. My name is Millen and I'm a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and university or college levels. If you are interested in getting help with your homework or if you're interested in getting some tutoring, check out the links in the description below. Cool, so I'm going to switch my screen real fast and we can get this physics party started. Cool. So the first question that we got on the menu today is actually kind of like 3 questions broken down, but no worries, we can still address them properly. So the first question is asking us, well, it gives us this situation where we have 2 particles, each with a charge of positive q. We don't really know what q is numerically, but we know it's just going to be q, and we can just, we can go about this and proceed just knowing q is a variable and is positive. So 2 particles, each with a charge of positive q, are located on opposite corners of a square. And the side of the square is d. So the question is asking, which is the direction of the net electric field at the point P, which is right here. Okay, so let's actually draw out this situation. Conveniently, I can draw out a nice square like this. Kind of represent this situation, looks good. Okay, so we know that here we have charge plus q. And here we also have a plus q. Nice and straightforward. Okay, so this is a square, so we can say that all sides are like this, and this distance right here is d. Okay, so what we're looking for is the net electric field, or the direction of the net electric field at this point P. Okay, so let's think about this for a second. Electric fields. Whoops, spelling is not my thing. Electric fields. Their direction is the direction that an electric field is going to point is the direction where a hypothetical positive particle would be pushed. So direction is where a positive particle would be pushed. So positive charges are repulsive. They have outwards electric fields. So positive is like this in terms of the E field. And negative charges have incoming, because opposites attract. So a hypothetical positive particle would be attracted towards a negative charge. Okay? Cool. And that would be the E field here. So attraction. Nope. This is repulsion. This is attraction. Okay, so now let's, given this that we know about electric fields, let's apply this to the square situation that we have right now. Okay, so you see the 2 Q's on the corner. The first one, it's a positive charge. That means the electric field is radiating outwards from itself. Okay, so let's take a look at the top left corner here. If we're going outwards, well, P is really just going to feel like it's straight downwards push from here, right? Right, because this is what the electric field is going to look like for here, and P is just going to feel it straight downwards because, well, given the position of P relative to that, that's just kind of what it would be like. And for the bottom right corner Q, it's giving out an electric field in all directions in the same way, and it's all outwards because it's a positive charge. And what point P is going to experience is just the electric field towards the left, pointing towards the left. Okay, so that's the situation that's going to be happening here. And what's really going on, let's write this in purple, the combination of red and blue. So the perceived E field at point P is the vector sum of the E fields of the two charges. So essentially what we have is we have that blue vector plus the red vector that's going straight downwards, and the result of this is the purple vector like this. This is going to be E net. We can say this is E right, and red could be E up. You know, the electric field caused by the upwards charge. So you can see that the E net is going towards the bottom left, the southwest, if you're thinking about compasses. So for here, the first answer that we'd have associated with the first part, I guess 14 in here, is towards the southwest, which is D. So, no solution to verify here. That's nothing to be worried about. We just know that the first one is going to be D. This is the direction. Direction of net E field. It is southwest, bottom left, whichever way you like to say it. Okay, cool. So the next part of the question is asking, what is the potential energy of the particle, of a particle charge Q that is held at point P? Okay, so now we're looking, well, we're gonna have the same situation, but we're gonna have, now we're trying to find the net potential energy from it. Okay, so let's talk about potential energy. Energy of charged particles. Okay, so the potential energy of charged particles is as followed. So the equation, we use the letter U often for potential and E for like the electric potential energy, because this is all coming from the electric force. So we would represent this as K, little q, big Q, just to specify that they are different charge values. Like the big Q is going to be associated with the with the top left and bottom right corners, and the little q is going to represent like the hypothetical charge that we're going to put there, and this is all divided by d, which is the separation between them. Another way that we could write k, because I know here in the option, in the multiple choice options here, they don't have the k, but k is also equal to 1 over 4 times pi times epsilon naught. Those are all just constant numbers, like we know 4 and pi, and epsilon naught is the permeability of free space, but we just know that this is like 9.09 times 10 to the 9. And yeah, it's just easier to write all of this out, but we don't actually even need to do the calculation, so don't really worry about the number. So when it's asking us, what is the potential energy of a charged particle held at point P? Well, let's think about point P. There's going to be a contribution of potential energy from the top and a contribution of potential energy from the right one right here. Okay, so when we want to add them together, we also realize that they're on corners of a square, right? So they have to be an equal distance away from them. So pretty much, when we want to find the net potential energy, so U net, this is equal to U up. So U up represents like the one with the red arrows, and this is going to be plus U right. This is the one with the blue arrows associated with it. So we find the potential energies of those individually, and then we add them together, and that will be our net potential energy as observed from a charge Q held at point P. Also keep in mind that it's positive, so it is like a repulsive thing, but we don't really need to worry about too much about signs because it's more of like a magnitude thing. Okay, so it turns out for them both, D is the same distance for their separation, and Q is the same, and the big Q is going to be the same as well, because the top left and the bottom right have the same charge of big Q. Okay, so let's write this out alongside this equation right here. So U net is equal to K Q Q over D plus K little q big Q over D. Okay, but you can see we pretty much have the same term twice, and they have to be the same because the D's are the same and the Q's are the same. So another way that we could write this is U net, the net potential energy as observed from point P, is going to be 2 times K Q big Q over D. Okay, now is that one of our options? Oh, all of our options are not written with K, are instead written with 4 pi epsilon naught. So we can write this as like 2. Instead of K, we can do 1 divided by 4 pi epsilon naught multiplied by Q, little q big Q over D. And this will be our net potential energy as observed from point P. Net potential energy. So this would correspond to one of our multiple choice options. It's going to correspond to D. So the first one was also D. The second one's going to be D as well. Cool. You see 2? Yeah, that's exactly what we got. Awesome. So we can move on to the third part of this question. The third part of this question, we got a line, and it's asking us, what is the ratio of the electric field strength at point A to the electric field strength at point B? Okay, so suppose I'm going to make the assumption that B seems to be twice as long as A. Okay, so I'll draw this out in a diagram to make this just a little bit more clear. So let's call this our line of action. Right over on the left side here, we got the charge positive Q. Okay, and somewhere along here we have point A, and somewhere along here we have point B. Okay, so the ratio of the electric field strength at point A and point B, well, we have to find the electric field strength of them individually. Okay, so actually maybe it's not great to make the assumption that it's perfectly halfway. We can give them different distance values, and then we can just have our ratio dependent on what their distance values are. So whoops, zoom back in. Let's call this distance between Q and A a nice thing that we can call that dA, nice and reasonable for a name. And the distance between Q and B, dB. That's a nice reasonable name. So if we want to find the ratio of their electric fields, we have to find what their individual electric fields are. So must find individual electric fields before finding ratio between them. Okay, so what's the electric field? We want to know the electric field formula, right? So this is the E field formula. We don't really need to worry too much about it being a vector because we are just like on a single line of action. But keep in mind, like if you want to do this in a 2-dimensional or even a 3-dimensional sense, you're going to need to use like vector components to it. But this equation is K, Q. I'll use big Q because that's the one of interest for here. KQ over D squared. Okay, so given this, we could do a little something like this. So for the electric field as observed from point A, well, this is going to be KQ over dA squared. For the electric field as observed from point B is going to be pretty much the same thing, except we're using dB instead of dA. Fairly straightforward. So this is KQ over dB, but you got to square it. Don't forget the squared. Okay, that's so this is for electric fields. You have to square it. Okay, so the ratio between the electric field strength of point A to point B, we're gonna want to do something like this. So ratio is going to be, we want to take the electric field strength of A and divide it by the electric field strength as observed from B. Okay, now we just got to sub the stuff in. So for EA, we have KQ over dA squared. Okay, instead of doing the division, we can just multiply it by the reciprocal. So dB over KQ, or dB squared, my bad. So this corresponds to EA. This corresponds to 1 over EB. Okay, and hey, would you look at this? You see the K on the top and the bottoms, they cancel out. We have a K upstairs and downstairs, but they neutralize each other. Same with the Q, because we were speaking with respect to have them having the same point charge, Q, on the line of action. They have the same Q, so that's going to cancel out on the top and bottom of here. So our final result is just going to be dB squared over dA squared. So this shall be the ratio of E field, the electric field, at points A and B. A and B. So as long as you know what those distance values are, you could just sub them into this equation and you could easily find the ratio between them. So if you find one, you could easily find the other with this little ratio here. Okay, sounds good? Sounds cool. So that would address all the questions in this, or that addresses all the questions in this little question set. So we can call this a day, or we could say, yeah, we can call this a question complete. So there is no solution to verify.